for the magnetos class. Partly because they're no longer, nobody's out there is making them. Now, what this does is, it's just a power supply. It's a power supply that puts out AC. Then it converts it to DC. And in converting it to DC, it then also uses a tank capacitor. So to draw just a brief schematic, what it is an AC power supply that puts out at 280 volts. Okay, it's going to go like this. Come out like this. Then we're going to put a diode on it that goes like this, and then right in here we'll take and put a big tank capacitor that causes this guy, the diode only lets current go one direction. Okay. However, so when I put it in line there, the AC, where the current's trying to go backwards, all it can do is start pulsing. Da, 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 stop, da, 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 stop. So as it's doing that across the load, what it'll do is it'll charge this guy up to a quasi state of about 400 volts. Okay, because of the size of the capacitor that I picked. So now at this intersection from here to here, I've got 400 volts DC. Kind of, it's oscillating DC, it's pulse DC. But, so then the next thing I'm going to do is I'm going to take and connect a voltmeter to here, which you guys can see the little voltmeter here, right? Then I'm going to keep the needle like that and say volts. So then across here, I'm going to also put a pretty high resistance resistor in here. Call this 50K, or, excuse me. We're going to call this 50K ohms, or ohms, like that. Now the purpose of this is it's going to cause a little bit of leakage while the circuit's up and running. That's okay. When the circuit shuts off and the power supply stops running, what I'm going to want is, I'm going to charge up a capacitor. I want that capacitor to be able to discharge through something other than me. Okay, because 400 volts
creates enough leakage to discharge the capacitor.
So this creates enough leakage to discharge the capacitor. Now I haven't shown you the other side of the power supply, but the other side of the power supply comes in off of 115, and then somewhere in there I've got a switch and a circuit breaker. Okay, and this is the transformer, the circuit breaker right there. So when I hit the switch, what I'm really doing is turning on the power supply, and it's kicking the 115 up to 280 volts, the AC. Then the diode and the capacitor are going to convert that to DC at 400 volts. Okay? So then the next thing I need to do is I'm going to need to have this guy kind of go out and be my negative test lead. This guy, I'm going to have to feed it through an amp meter and have it come out to my positive test lead. The problem is at this point is there's nothing to limit the amount of current. Now the devices that we're going to be testing call for a leakage of no more than, I think it's 7 or 8 milliamps, something less than 10 milliamps, okay, at 400 volts. So I'm going to have to limit the current because I have a pretty good suspicion that you guys might accidentally short the leads. Because when I look at the capacitor here, what are the leads? There's a lead here and there's a lead here, right? No, this goes straight through. This is how electricity gets into the magneto. One of the leads is the case, The other lead is this passage going straight through to here. But there's a propensity for you guys to hook up here and dead short everything. So I'm gonna have to limit the amount of current this thing can produce. Okay, well, if I do a bunch of math on this, what I find is this, I'm gonna want it to be 10 milliamps on my meter movement. Okay, meter movement, 10 milliamps. And then I'm gonna wanna stick a resistor in here of approximately 150K. What I found was that was a little bit too high. So I actually then took and paralleled another, no, I'm saying that wrong. Actually, you know what? This was 150. What I need here is 50K, and then I paralleled another 150 across it. And that got me down to about 46K. Somewhere there, 40K. Actually, yeah, it was 39K, now that I think about it. That gave me a full 10 milliamps movement when I short the two leads. Now what I'm going to do here is I'm going to hook this up to the capacitor, which is what that is. If the capacitor is working right, the dielectric through here will not allow 400 volts to leak through. Okay, and the test is, and I forget it, 7 or 8 milliamps at 190 degrees, because that's how hot it is in a magneto. So they tell you test it at 190 degrees, you know, check to see this isn't measuring the amount of capacitance. That's a different test. This one is just saying, let's subject it to 400 volts, which it calls for, and make sure that it doesn't leak above 7 or 8 milliamps. Okay. Now, when I first hit the voltage going on, this guy isn't charged, right? So I should see a very quick surge on the amp meter as it tries to charge up. But once it charges up, it should drop down. Probably will also see a very slight dip in the voltage briefly. And in fact, when I dead short it, I'm going to see probably going to drop down to 350 or 380, something like that, because voltage does have a limitation on it. Okay, so let's see if we can do this. Plug it in. Oh no. All right, so now, I don't know that I can I shine this on to where you can see both meters? Well, you can sort of see that you can't really see the accuracy of that one. But there's 400 volts there. And then this one right here goes 1, 2, 4, 6, 8 to 10 milliamps. Milliamps square, and note it's DC or pulse DC. Okay, both of these are volts pulse DC. Right? So now the first thing I'm going to do is I'm going to dead short these guys just to make sure that I've got at least, I think the value is 7 milliamps. If I can't produce 7 milliamps and dead short, then I won't be testing this capacitor at whatever the spec is. Okay? You'll see that the voltage doesn't quite make it to 400. Okay, we ready? Are we ready? Mm-hmm. Oh. Okay, hold it on there, and you can see how the voltage isn't quite up to 400, and it looks like we're putting out about not quite 10 milliamps, 9.8 milliamps, somewhere in there. Mm-hmm. Okay, so dead short. If the capacitor was completely shorted, fried inside, that's what we would see. Okay, or if it was leaking, whatever the dielectric in there was leaking badly, we'd see it get up to there. Okay, so now what we're going to do is we'll hook it up to across the capacitor leads, right? If I hook it across here, what's it going to do?
Dead short.
It's going to act like a dead short. Well, let's test that.
We got 9.8 milliamp.
Sure enough, dead short, right? Okay, I'm going to let it sit for a little bit just in case I'm wrong. Okay, so now we're going to test that there, and then I'm not going to hang on to it because that's 400 volts. Believe me, I've tested it. It does. It'll zing you. Okay, so now watch the amp meter. Okay. Okay. Well, there's a little delay. So hold it down. See it pulse like that? And the voltage up there. Now watch what happens when I let go. Oh, see that discharge? That's the capacitor discharging back through this resistor here. Okay, until it does that, don't touch the leads.
Cause it's gonna discharge through you.
It's gonna discharge through you.
You'll be the ground.
Exactly.
Yeah, you'll be the ground.
At 12 volts, if you get your hand wet, 12 volts, you'll feel it.
Yeah. Give us an example.
400 volts, you don't. Okay? Yeah, come up here. Why don't you do the test, you know?
Volunteer.
Yeah. Okay, very mild taser. It's a very simple power supply, but it does the job. The problem is,
Taser works?
Hmm?
Is that how a taser works? With the capacitor and
essentially.
all that? Okay.
only much higher voltage.
The charge of capacitor.
Higher
and then
voltage.
Stick you with the
What is
leads,
that,
right?
like 1,000?
I think they're higher than that. They're like 20 or 30,000.
Oh, really? Wow.
Well,
Look it up,
the
but they're
average-
they're in the 10,000, you know, the 5-digit numbers. Okay, so I could buy a tool that does the job here, but it was like $12,000 and it did a whole bunch of other stuff, which
Which you don't need.
I made this for $100. And the simplicity in it is I know how to order parts, A, and I know how to do Ohm's law, B. Okay? Other than that, that's all you really need to know to figure it out. Now, what happened is I got in there and I knew this value is going to be a little bit wrong. Partly because I'm getting some resistance from some of the other components. Okay, I knew there was going to be a little bit some values wrong, so I was prepared to have to put. I calculated this to actually not give me quite enough milliamps, so it gave me about 6.5, 7 milliamps. But I knew that if I bridged another parallel resistor across there, I'd be able to get fine-tune it. I also could have bought a fairly high-powered variable resistor and then just adjusted it to whatever I needed. Okay, that was quite a bit more expensive though to go that route. That would have been like $8 more. Okay, now the other side of that is do the math on 400 volts at 10 milliamps. Okay, the wattage of each one of these, this one actually, it only needs to be about 2, but I bought a 5 watt. Here, these are 1 watt, the bleed down's 1 watt. They're fairly large resistors because 400 volts. Same thing here, that guy's 1,000 volt at 5 watts. And these capacitors are, I think, 450 volt capacitors.
So the upshot of that is that'll test the capacitor.
That'll test the magneto capacitor as called for in Bendix magnetos. The S200 magneto manual. Okay. Now, if I really wanted to do it well and make a whole bunch of different values, what I would have done is I would have put a value in here that allowed me to put a different values of voltage drop across here. The other thing I could have done is this guy, as a transformer, actually has several windings in there. I only use the 280 winding. It has a 140 winding and a lower winding. So I could have put a multiple selector switch and had various voltages. I could have gone for 400, 200, and I think 40 volts, something like that, had I wanted to. Okay, I don't really care. I didn't want that many options. Students are going to be using it. I only want one option. Okay. Now, when you guys take the magnetos class and you do that, it's like that turbine igniter out there. It can hurt you. Don't attach the test leads to yourself or grab the capacitor while it's charged. Okay.
Always.
That thing up there, this is milliamps. The turbine igniters, they're putting out in the amps, and that'll stop your heart cold. Okay, alrighty. Here. There. You need. Do need this. No idea. Optimal resolution notification. Good God, that's good to know. It's actually terrible resolution. Everything look funky.
Yeah, something's right.
Okay, I have that we were just talking about voltage regulation. So what we'll do is we'll try to get through, maybe get into schematic, we'll get through, finish up AC theory. We'll probably do a quiz next week, so we'll review for that. Then I want to, I do want to spend a little bit of time prepping for the lab, so I'm gonna go through and look at some of the tools, available tools, and then potentially, what am I trying to say? Oh, kind of run through the project, what the first project's gonna be. Okay, so and then depending on where we're at, we may or may not go. We may be close enough to end of lab that we will just go home instead. Okay. I have that we stopped right there. Everybody remembers how this guy works.
The Y and the delta.
The Y and the delta and how the bridge rectifier works. Okay, we're gonna pull in electrons on the red branch, which is actually gonna be the positive branch, and run them through the diode against the direction of the arrow, and then push them through the set of coils and then back out a different branch and push them out the blue side, which in this case becomes the negative side.
That's
Right? Okay. So I have that we need to start right here. Okay. So the controller for these guys isn't that complicated. Thanks to that thing that we were talking about through the last series of lectures called hysteresis. Okay. So the simplest way to deal with this, remember we're going to regulate the output of this. We can regulate the output by changing the current and have the voltage do whatever we want it to do, whatever it wants to do. That's going to cause our brights to get light and dim and all kinds of weird funky behavior, right? So in truth, what we really want to do is regulate this thing, keeping the voltage fairly constant, irrespective of what RPM occurs. Okay? We talked a little bit about the fact that the RPM is sort of out of our control. If it's an AC generator, we want the RPM to be fixed. We'll talk about why when we go back to the AC theory. If it's a DC generator, almost always it's bolted onto an engine that has its primary mission is to stop and go. So its RPM is going to be changing all the time. So that means the only thing left we can do to control the output of this thing is to control the amount of magnetism produced by the field. So we can do that by turning the field on and off again. And isn't the field just like a light bulb? Okay, it's a big inductive coil. But in the circuit, we'll draw a new circuit. In the circuit, we'll just do a battery. And we're going to go like that with a switch. And our field is just an inductive coil, right? Now there's other circuits. There's the armature, there's the light bulbs, there's the landing lights, gear motors and everything. But for the purpose of our discussion, all we really need is the field to talk about. Now there's a connection here. Remember we said there's a slip ring here and a slip ring here and a few things. But ultimately, it's still a circuit just like a light bulb. And I have a nice big magnetic field around there. Well, if I turn it off, the magnetic field is going to collapse, right? Mm-hmm. And hysteresis says it's going to take a certain amount of time to collapse. It's not going to instantly go away. It's going to take a while. So if I turn it back on again, it's going to start building up again. Turn it off, it's going to start collapsing again. Turn it on, it's going to start building up again. Turn it off, it's going to start collapsing again. Right? So if I can start turning it on and off in a fairly cyclical manner, I'm gonna have the magnetic field sort of sitting there. Now, if I have more off time than on time, it's gonna start collapsing and getting smaller. If I start cycling to where there's more on time per off, on, off, on, off, okay? More on time, it's gonna get bigger and bigger. However, during those periods where it is turned off, current is gonna stop flowing on this side, okay? It's gonna try to keep going here, but it's gonna stop flowing on that side. So during those periods where it is off, field's actually gonna, it's not gonna use any current then. My other option would be to go like this and put a variable resistor in there, okay? But in here, as the resistance goes up, this guy's gonna get hotter, right? So overall, this circuit will use more current than the other circuit by a little bit, okay? Given that we're trying to produce current, not use current, we probably don't want to do that if we can avoid it. Now, in bigger units, when you start getting into large generators, it's the variable resistor or analog type is the only way to go, because every time I open that switch and close it, there's going to be a little arc. Well, my field needs to be at 10 or 15 amps. That arc is going to wipe that switch out pretty quickly. Okay. On the other hand, if it's a small unit, like these small little 40 or 50 amp units, the field only puts out about an amp of current. It doesn't need a whole lot. So that thing is going to last a long time. So the switching design is going to be smaller. The big resistor design, okay, big resistor, analog resistor design is going to be quite a bit bigger and for bigger units, 200, 300, 400 amp generators. So, little bitty mechanical switch goes click, 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 click. It actually goes bzzz, pretty high rate, okay? Because what's going to happen, this guy's going to be measuring voltage. And as the voltage goes up, it says, okay, I'm going to open. Voltage starts, the output voltage from the generator, okay, generator's here, the output voltage here starts going back down. It says, oh, okay, the voltage is going down, we're going to turn the field back on again. On and off and on and off based on voltage. So if it's a 12-volt battery, sort of like I've got drawn there, then our set point's going to be something above 12 volts. Right? The truth is, the lead-acid battery, as we talked about, standard lead-acid battery likes to be fully charged at 12.68 volts. We don't want to super overvoltage it, so taking it to 16 volts probably isn't good. However, not too bad if you keep it about a volt above. So we're going to take the set point of this regulator and say, let's call it 13.68, 1 volt above. Okay? Well, right there, and this is going to be true of all of them, it's slightly higher if it's an AGM or other types of batteries, but that right there tells you how to diagnose everything. If you fire the engine up, get the thing off, everything's supposed to be working, and put a voltmeter on the battery, and it's putting out something above battery voltage, it can't be that the battery isn't working, okay, or that the charging system isn't working, because the battery can't produce more voltage than it can produce, right? On the other hand, if I do that and I've got battery voltage, nothing else, then it may be something's wrong.
Means the
up here.
regulator's not working?
Huh?
Means the regulator's not working?
Regulator or the generator or something else something isn't outputting. We haven't talked about how to test that, how to sort of determine which is which. Okay, it turns out that I put this right here, okay? We're gonna call that positive, we're gonna call this negative. I could also put it here instead. The light bulb doesn't care where the switch is, does it?
No.
Okay, so positive control or negative control. There's a written on that.
Yes, there is.
It's that simple, guys.
Just
Don't
where the-
complicate
Where
it.
the switch is?
It's literally where the switch is relative to positive in a DC circuit or negative in a DC circuit.
Say that again. Say that again.
Positive control says I control on this end, positive side.
Control with the switch.
Negative control says I control on the negative side.
Okay.
Okay, someone change the rules on you guys. Okay, I'm going to put a switch right here. And then I'm gonna put a magic box switch right there. Okay? This right here is your injector, one of the injectors for your car. This here is the switch that gets closed when you turn the key on. Okay? This switch right here is the magic computer that controls when the injector fires. Okay?
So that
Now it's negative control and positive control.
function of both.
This for the human interface device, this for the digital computer device. Part of the reason we do that is the transistor that we're going to use in here, it actually goes to ground. The transistor that we're going to use in here, power transistors as a preferred value are always made in the NPN style. Okay? They need to be on the negative side of the circuit so that the rest of the brains of the computer can operate in the positive side of the world and with normal polarity. So it's very, very common for computer outputs to control on the negative side because their brain operation is always done in normal polarity. So I just gave you some input on a project written that you guys are going to have to do. Does the light bulb or the injector or the field coil or the anything care?
No.
Where the switch does not care. Okay. Now in the world of electromechanical devices, it actually, this doesn't care, but the device that's controlling does care. Okay? So if it's just a little voltage sensing coil, and all that has to happen is the coil that goes through there, regardless of which way it's wrapped, is going to cause a magnetic field that's going to open this, then it doesn't really matter which way the current goes through this thing. On the other hand, if I've got an analog device where the directionality of the current going through the little voltage sensing coil determines whether or not it pushes against the spring or relaxes against the spring, then that one really matters. Okay? And it's just like taking a voltmeter. What happens when you take your Simpson and hook it up backwards?
It drives the needle the other way.
Doesn't the needle just go pop, 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 and bounce
Yeah.
there? Okay?
Yeah.
That's not working for you. So the voltage sensing part of this type of device, it can't be plugged in backwards. But the variable resistor part doesn't care. So because of that, they came up with this whole vernacular for field regulators. Type A and type B and all this stuff, which is really kind of
I
stupid.
got a question about the spring. Does it wear out after a while when you go?
Does what wear out? The spring?
Yeah, the voltage spring when it's going that fast.
The spring actually is usually not the thing that fails, it's the contact points that fail. Because remember, they're arcing every time,
So that
a
means
little
they're-
bit.
Whatever they're made out of, they're losing a little bit every time.
A
Right?
little pit, a little molecule or two is,
They're not made out of carbon.
So
are they?
eventually,
Huh?
The carbon. They're not made out of carbon, are they?
no, they're made out of very hardened steel metal. The little contact end is.
so they wear out enough, becomes a great big resistor. And the
Oh,
current does not want to flow when they're touching.
what happens more often is as they start arcing, they start pitting, as they start pitting, the carbon starts developing just from surrounding dirt in the atmosphere. Then the carbon starts adding resistance to the circuit, and eventually the current being fed through there starts declining, so it tries to do more on time.
Hmm.
Okay? Okay, more on time means more current, means more, so they do eventually fail. So mechanical, the mechanical switching device does eventually fail. However, there are some other ways of doing business. Particularly if I don't need some of the other components. Now in a generator, standard DC generator, I'm going to need a couple of other components. And we'll come back to this guy. But one of the components is going to say, for a very short period of time, a DC generator can put out way more current than it was ever designed to put out. It will eventually limit itself. But it can, for a short period, it can put out a whole bunch of current, can damage things. So I need something to turn off the field if suddenly the current goes way up. The other thing is a DC commutator style generator is a motor being run backwards. So if I ever have the situation where the battery voltage is higher than the DC generator voltage, then the battery is going to try and motor the DC generator, like when the engine is shut off. So one of the things I'm going to have happen is when the engine shuts off, this guy's going to have to disconnect the generator from the rest of the bus. Okay? So we're going to have some other components. If it's an alternator type, where I don't have all that commutator stuff, I've just got my bridge rectifier, I don't have to worry about the reverse current, do I? The diodes won't let it go backwards.
Already going in one direction, correct?
And the diodes prevent reverse current. So I get rid of that. The alternator we talked about already a little bit, it's self-limiting because of armature reaction. They both are, but the alternator very quickly will hit its limiting value. So it cannot overcurrent. Now the one thing an alternator can do is it can go over voltage if something goes wrong with the regulator. So there are some systems, particularly 24 volt systems, that do have overvoltage protection, or at least an overvoltage light that comes on, because you might not see the voltmeter going, bah! Okay, a big yellow light comes on, something like that, big red light. Otherwise, all I need is the switching device. Well, now that we have invented diodes, we can tack a couple of diodes together and invent a transistor, which can be an electronic switch. There's no contact points open. So an early stage device, they digitized it somewhat, but still used the mechanical switch. Then later on, they said, hey, wait a minute, we don't need that mechanical switch. Let's have a little circuit, measures voltage, and it controls this big transistor. And in fact, this big transistor acts in an analog manner, just like this big carbon pile regulator does. Okay? And I get a little bitty circuit here that allows me to, a resistor that allows me to adjust its set point voltage. Okay? The downside of this is, remember we said when I put a big resistor in there, it gets hot? So it has to have this big plate for cooling. So they then figured out, well, wait a minute, if we go to the switching technology, where it just turns it on and off, and on and off, and on and off, turns the field on and off, when it is in the off period, there's no current flowing. And when it's in the on position, we turn the transistor on full blast. So it has very low resistance. So it doesn't get very hot. So now we can take, and the wires are a little bit fungoid on me, but we can take and make it really, really small, and this little bitty transistor here, which uses this plate as a heat sink, is the thing that turns on and off. Okay? We can now make this so small that we can package it inside the brush assembly and make them all combined into one thing. All right? Oh. Okay, so solid state switching, solid state analog, analog resistive, and then mechanical switching are the three types. So in this case, it looks like I've just shown you, I'm now showing you this circuit right here. I'm not showing you the master switch or anything else, but I've now put a regulator between the bus and the field goes to ground. I could also take that out and slide it in here. Okay, I might have to do a little bit of rewiring to make that work. And then on the other end, it doesn't change at all. Okay, so what's going to happen if the RPM goes up?
It's going to increase incineration.
Well, if I've still got, I haven't turned anything on, so the resistance of the rest of the bus is the same, RPM is going to go up, voltage is going to try going up. The regulator is going to say, no, 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 no. We're not going to let the voltage go up. We're going to turn the current to the field down some to keep the voltage right at 13.68. Okay? Now you decide, night is falling and I'm scared, so I'm going to turn everything on. Click, 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 click. Everything turned on. Okay, engine RPM is the same, but now I dropped the resistance significantly, right? Well, because I dropped the resistance significantly, the battery's saying, oh man, I got to put more current out. So the voltage drops. Regulator says, no, 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 no. We're going to crank the field up to keep the voltage at 13.68. So regardless of whether I'm change in RPM, or change in load, the regulator says, either one of those change the voltage, we will correct for any change in voltage by affecting the amount of current going through the field. Okay? We do that either by variable resistance or vary the amount of switching. And usually the switching is fairly repetitive. In other words, it turns on every thousandth of a second, but the amount of time it stays on varies. Okay. So let's talk about, and I'm not going to test you guys on this, but here's an example of a digital circuit that's not too dissimilar from this one right here. Not too dissimilar from that one right there. So you're going to recognize some parts. Okay, you guys recognize the bridge rectifier, right? You recognize the stator or the armature output. Okay, that's kind of the same. Got the field rotor with the little slip rings. That's all the same. One of the things we did is decided let's take and make another little bridge rectifier coming off of here called the diode trio. We're going to use that for being the source by which we measure our actual voltage, a real accurate measurement of voltage. So we're not going to trust what goes out here in this big long line up to the main bus and all this. That could be problematic. So we're going to come up with our own little bridge trio, and that point of voltage, or this point of voltage, is going to be the voltage we're going to measure and react to. Now note, we've got a field. Coming off of the field, we've got voltage right here coming from there, or potentially coming from the battery to this point. And we're going to send it out here to the field, up through here, up through there, through the field, back here, back down to here, into that point right there. Okay? So the field has got positive electricity at all times. Okay? It needs, if I connect this straight to ground, the field will go full boat. Right? Positive coming in, if I take and attach that to ground, field's on full blast. So if you look at this transistor, the transistor will connect it to ground. So all I have to do is turn this transistor on. Well, since the output is in for negative, the input also has to be in, which means the control, okay, or the gate has to be a P. So if I make this guy positive, that'll turn the transistor on. Okay? So how do I make this guy positive? Well, there's a couple of ways. One of the things I can do is I'm going to put a very high resistance, maybe 10K resistor here, that says if something's going on here, it'll cleanly go to ground and shut the transistor off. But if I start sending a little bit of current down here across this diode, some positive down this diode, it'll turn it on. So these two cause the transistor, instead of being an analog, it switches it on. Boom. It clicks it on. This diode is going to take about a 0.7 volt to drop across it to start conducting. So that means if I cause this here to go positive, this transistor is going to turn on. Right? If I cause this to go positive, well, I can get positive across this resistor here. Right? And this guy, this transistor here, if it's turned on full blast, it's going to cause all of this to go to ground, which means that the total voltage drop across here is going to be right across here, right? So this guy will act like it's ground, so this won't be positive. But if I start to close this transistor, now this becomes the big resistance here. This, as a voltage divider, the voltage here starts coming up. It'll come up to some point where suddenly it conducts across there and turns that guy on. So this guy here, also an NPN. If I make it positive, this is where it gets a little confusing. If I make it positive, it'll turn this one off. If I make it negative, it'll turn this one on. Now this guy here is being fed, the P right here is being fed by a Zener diode. I don't know what the voltage is of that Zener diode, but the Zener diode says, unlike a regular diode where electrons can only go one direction, and it takes about 0.6 volts to get it to go one direction, it'll allow them to go the other direction above some voltage. And they make Zener diodes at different values. So let's say it's 5.6 volts. Okay? We'll allow anything above 5.6 volts, we're going to allow electrons to travel across here. Okay? Now we're going to have a voltage divider across here. There's actually a parallel here, but this is a voltage divider circuit. So let's say we're at 13.68 here, drop down to 5.6 here, and then 5.6 to ground. Okay? So if the voltage starts going above 13.6, the voltage here goes above 5.6, causing electrons to go to here, causing this to go to P, causing this to go to ground, shutting this off, shutting the field off, causing the voltage up here to start dropping. Okay, did I lose most of you?
Yep.
Yeah?
Pretty much.
So let's try that again.
Oh man, my head's hurting.
Let's try that again. Okay, this is the way electronics are. It's kind of all around the mulberry bush, right?
Right.
Okay, so we're gonna say, up here, I got battery voltage, whatever that is.
All right.
And we want a set point at 13.68. We're gonna have a voltage drop, right? Voltage drop to something, voltage drop to ground. Okay, that's just a series circuit, although I've got two resistors in parallel. I do that so that I can adjust this some out of the factory. Okay? Remember I said I can adjust this some? This little guy right here is my variable resistor here. This says I'm not going to let it completely, I'm not going to go completely to zero because that would cause bad things to happen. But
So the resistor is effectively like a backup in case your variable.
no. So it's another way of saying, so no matter what, if I went all the way to infinity resistance here, really high resistance, suddenly this guy would go way high. And then that would really turn the field on full blast. So I'm only going to let this, with this resistor here, I'm only going to let this thing range from, let's say I'm dropping half of my voltage. I'm only going to let it range from, say, 5 volts to 6 volts. Okay? At anything above 5.6 volts, I'm going to want the regulator, the field to start coming back because I got too much. Anything below, I'm going to want it to start coming back on. So this parallel keeps the bottom end from being, going down to, zero, going way up to full battery voltage, right? So right here, let's say this drops down to 5.6 volts. If I go above 5.6 volts, because this is above 13.68 volts, I want the field to start backing off, don't I?
Yes, sir.
Okay, so above 5.6 volts, this guy starts conducting this way, right? It starts conducting this way. That causes this NPN to P to start going positive. As it goes positive, it turns this transistor on, which now I start getting current coming this way, but because I've got a fair amount of current going this way, now I get a big voltage drop across here. So this goes negative. When this goes negative, I'm not getting any P here, so this NPN shuts off, which shuts off the field. Okay, so we're getting an action reversal here. Okay, one is turning off, the other is turning on. That's turning on to turn that off. When this turns off, it turns that on. That's where you guys are probably getting a little confused. But that's the way they chose to do this. Okay, this is actually fairly common arrangement. A lot of the Bosch alternator regulators were set up this way.
Sorry if this is obvious, but what's that right there for Charlie 1? That's got a.
This guy right here,
Yeah, thank you.
all this does is when these guys pop on and off, switch on and off, it creates a little bit of a surge. So this capacitor allows any AC surges to go to ground.
Okay.
Because you want all of this to stay DC. But any weird pulse, particularly coming off of this guy right here,
It's gonna
Um,
surge, and then it's gonna go straight through.
It'll just go straight to ground. Yeah.
Capacitor's gonna take it and then send
Yep.
it to the ground.
It sends the energy straight to ground. Okay. So all that does is make sure that the voltage here is nice and stable and clean. And in fact, this is pretty rudimentary. This will work, but more later models have done quite a few things better. Now also note that somehow we got to turn this puppy on. When I turn the key on, I got to have something come on and supply enough power to here to get things up and running. But once this gets up and running, I'm now producing enough power to where most of the power for all of this in the field comes from right here, right? Meanwhile, back at the ranch, if in fact this isn't working well, this guy isn't putting out any, what's going to happen is this guy is going to be on to ground, which will turn this light on, the idiot light.
That's the
If
thing.
everything is working,
Tells you the field's not working.
this will become positive. This will be positive. Positive, positive, 12 volts. There's no voltage potential across the light bulb. It goes out. It's hot, but it's hot on both sides, so it goes out. Now, what happened in the early days was that's all they did. Everybody's good to go. Drive around until the light bulb burns out. Then your generator stops working. That's not so smart, is it? So there's a second pathway for a resistor. So if it burns out, it will still activate and light up the generator. Okay. Now this, I'm never going to test you on the Slotsky type transistor here. But it's at some point, if you ever want to play with electronics, you're going to have to understand how NPN and PNP transistors work. Now, I don't dive too heavily in this class, but the airframe class, I do dive a little bit more into how they work. So note that this guy right here, D2, that's a Zener diode, and their most common usage is to measure voltage, to sense voltage. In this case, that's the guy that says our voltage is dropping low, turn the field on. Our voltage is going up, turn the field off. Okay? And these guys, unlike other ways of doing it, these guys don't vary with age. Most of the time what fails in this whole circuit actually are going to be these brushes right here and then one of these diodes out here. Although occasionally I've seen the diode trio fail. They don't use the diode trio too much in the aviation world. I don't think I've ever seen it, but it's used extensively in the automotive world. And note the big yellow line going all the way around. All of this is contained in the alternator now. Okay, the slip rings, and in fact, usually what happens is, what happens is this whole component, all right here, is all bolted together. Actually, not the diode bridge. That's all bolted into one component. That's the assembly that holds the brushes into the slip ring. A couple of 3 screws hold it in place. The regulator's all internal. Their internal connections are made. The field sits there. The bridge rectifier sits there. And this bridge trio, the diode trio, is actually hard mounted into the rectifier plate. Really common. All right, so this is just showing, that was an analog type. The more sophisticated type, like this one, what it's going to do is it's going to go on, off, on, off, on, off, like a metronome. Okay? When it turns off will vary. Okay? So here, it's about 50% duty cycle. There, it's on only about 20% duty cycle. Now down to about 10% duty cycle. Then coming out to here, it's on, 80%, 90%, back to 50%, down to 10%, etc. So based on voltage, it's going to spend more time on than off. However, it's going to repeatedly turn on the same, call that 5,000th of a second. And then it'll be on for one period of that 5,000th of a second. Now, this is important to us Because when you're getting RF or noise, audio noise off of a generator or an alternator, there's really two kinds of noise. One kind of noise will come off of the diode bridge right here. Note the big capacitor here. One kind of noise will come off of here, and hopefully you're going to send it to ground through the big capacitor there. If you're hearing it and it varies with engine RPM, it goes up and down in tone, it's probably noise coming off the output of the armature, right? Maybe that capacitor is starting to fail. There's a bad connection somewhere in here. Something's going on. If in fact you're getting noise, now either way you know it's the generator, because when you turn the generator master switch off, the noise goes away. Turn the generator master switch back on, the noise comes back. Same thing with the field. You turn the field circuit breaker off, noise goes away. Well, both of these are going to shut down. So, but if I get a change in tone with RPM, then it's probably the output side of the generator. If I get a very fixed tone, turn the field on, generator on, whatever that noise is, and it doesn't change with change in RPM, then it's probably being caused by the on pulse, okay? There's a little bit of a spike, and it may not be on this circuit. It may be that the wire is running next to the antenna of the radio or something like that, and there's a little bit of coupling going on. Okay. So voltage regulator noise tends to stay constant in tone. Generator output noise tends to vary with engine RPM. Okay, and as I said, when they're dinky little guys, they can be internal to the regulator or to the alternator. In the world of airplanes, because we went down the rabbit hole of commutator style generators and the voltage regulator being separated, all the certification processes to put them in internally, the world never did that. They just didn't bother doing that. Where they needed one, actually I have a solid state one somewhere. Yeah, I'm not seeing it, but what they did is, they sort of did it in this one here. What they did is they kept the same base, and then they got rid of all of this, and it's just a funny little circuit board sitting in there with a big cover on it. It looks exactly the same from the outside. Has the exact same connectors out there. They might have made it a slightly different push on, but they made it to where it bolts into the same spot. Okay. So in a lot of cases, they just kind of went with the same thing, even though they didn't really need, they could have made it internal. In the world of the automobiles, they said, look, diode rectifiers fail, voltage regulators fail, brushes fail. But from the maintenance perspective, rather than change each one of those independently, let's put them all inside the alternator. And when any one of them fails, you just take the whole unit out, put it in a box, mail it back, put an exchange unit back on, you're good to go. And bar none, if you're going to overhaul a unit, you're just going to replace them all anyways. New brushes, new voltage regulator, new brush assembly, new rectifier, new bearings, clean up the slip rings, test everything else, put it all back together. Okay? Do a bench run. I don't know if I've done thousands of them, but it's definitely done hundreds of them.
Can you repeat that, what you said about if the noise thing and the, whatever you were talking about?
Wow, that was like 4 chapters ago.
I know, but I was trying to.
Okay, so
If
it's coming out of the alternator,
if noise.
the frequency of output is going to vary with engine RPM. Okay, so if you're getting some noise, it means either that capacitor is failing or is mismatched or something else is happening there. You got a connection starting to give you some problems, right? If it doesn't vary with engine RPM, but definitely goes away when you turn either the generator or the field switch off, then it's probably the voltage regulator giving you noise. Okay? Now, if the noise doesn't change whether the generator is turned on or off, it's probably not the generator or the voltage regulator. It's something else. Okay. So, again, in the world of automobiles, you can see the voltage regulator occasionally attached on the ground side. There was, in fact, most of the BMWs, Robert Bosch, for some reason, in those cars, they had them on the negative side. But it's less, it's fairly uncommon. In the world of airplanes, all the bigger airplanes, they actually typically did put them on the ground side. The big bombers, etc., with the carbon pile type. With the newer airplanes, they tend to all be on the positive side. Okay. So, yeah, this is now showing a little bit better connection diagram. Then, okay, so I'm going to talk about this a little bit in one context. The test, there's two different tests you can do. The physical test is exactly the same. One is when you're trying to reestablish permanent magnetism in a commutator style unit. The other is when you're trying to diagnose, is it the regulator or the generator? The way I'm going to hook up the circuit is the same. But in one case, I'm going to call it full fielding. That's what I'm trying to diagnose. And in the case of the trying to flash the field, I'm going to call it flashing the field. Okay, two completely different purposes, but I am the human test lead. If I want to know whether or not this voltage regulator is working, can I just bypass it? If I hit the switch here and the lights don't come on, click, whoops, oh, I got shut all the way across. Oh, it's right underneath. Thank you. One way to check whether or not the switch is bad is I could just bypass it, right? The lights come on, but they don't seem to be coming on, bypass it. Well, I can do the same thing here. If this thing isn't putting out voltage, and I'm only seeing battery voltage, I am the human test lead. Click, I bypass it. Full field, this guy. Go to full magnetism. Okay, I'm going to need to be a fairly strong test lead. I'm going to need to be 3 or 4 amp lead that can handle it, right? But I'm just going to bypass it. Or if it's on the negative side, I bypass it. Okay?
Bypass that, I mean, the voltage is gonna be much higher,
It's going
correct?
to go way up. So as I bring the RPM up, I might see 18, 19, 20 volts.
You're not regulating the field.
You're not regulating.
Okay.
So if it comes skyrocketing up, I know the generator is ginning, right?
Right.
If it doesn't come skyrocketing up, and by the way, I know the ginning is ginning and the voltage regulator was the problem. If in fact I bypass it and it doesn't come skyrocketing up, then probably the generator is the problem.
Oh, okay.
Okay? You with me?
Oh, yeah,
Somewhat.
somewhat, yeah.
I need to know, is the switch bad or the light bulb bad?
Right.
Okay, so in this case, if I bypass the switch and things get better, then it was the switch that was bad.
Makes sense.
If things don't get better, then in all likelihood, that field went full blast. Okay, either this is bad or I've got a thrown out brush somewhere, something else is bad, but either way, it's got to come apart. Well, in the automotive world, we don't really care, do we?
Take it out,
Because
change
it's
it.
all got to come out and be replaced anyways, right? So we're going to take the whole thing out and throw it away or replace it anyway. So, however, I'm one that kind of likes to really know what's going on. The best way to check it is with an oscilloscope. I'm not going to talk about flashing the field just yet.
I was gonna say, thought that was the answer.
Oscilloscope is a good way to do it, but you can get the basics with just a standard voltmeter. The hard part is going to be, in the case of an internally mounted voltage regulator that's deep inside the bowels of an alternator,
Being able to bypass.
it's impossible to bypass it, right?
Cause you would have to take it apart to do that, now
Yeah.
it's not running.
That's right. Okay, so the two, other than brushes failing, and actually surprisingly, regulator or rectifier usually fails before the brush fails. Brushes fail, unless you're like me, who I've actually one alternator I'm running. I've gone through 4 sets of brushes, and that puppy's been around a long time. Well, I'm just trying to see, you know. I've made it way over capacity. It's 100, I think it's 110 amp alternator, and I've got a grand total of like a whopping 22 amps on the circuit, on total circuit. So, but by going overboard, it's not any bigger, it doesn't weigh anymore. I think what I've done is I've figured out, I'm proving the common cause of rectifier and regulator failures is too much load. So, if I full field the alternator by bypassing the regulator, I should see something like 17 to 23 volts at higher RPM, or 34 to 40 volts if it's a 24 volt system. Okay, it's going to go up there quite a bit. You don't. All you're really trying to say is, I'm now at battery voltage. I bypass it. It goes up. I give it a little RPM. Whoa. Okay, that's it. Stop there. You established the voltage regulator is a problem. Now, in the world of airplanes, where these are separate, yeah, you just buy a new regulator, slap it in there. Everybody's good to go, right? Wrong. You don't ever make that decision for the customer. Don't ever do that. It's gonna bite you. It's gonna bite you in terms of damaging the relationship you have with that customer. Always make them make the decision. Put it back on them. And they're always gonna go, well, what would you do? Here are the consequences of this choice or the other. So look at the logbooks. Man, the alternator is 27 years old. The regulator is 22 years old. The battery is 19 years old. Look, really, we ought to be replacing all of these, just based on age alone. I know the regulator is bad now, and we can put a new regulator in, and it will probably work. But you're going to be back here soon enough. Okay. I also know the battery is dead in the door now, so we're going to have to do it. So battery regulator. The generator may go belly up, you know, in fairly short order. We don't know. But make sure they're aware of it, and make sure you acknowledge that they're aware of it somewhere on your work order. This isn't the world of FAA regulation. It is the world of Department of Consumer Affairs for the state of California regulation. And it doesn't matter. People get a little lost and confused in this. It doesn't matter whether you're working on an airplane, a car, a Maytag, a blender. If you are working for profit, servicing any piece of equipment, you have to follow the same rules. Okay? The only difference is in the world of automobiles, there were so many crooks. They designated an entire agency, Bureau of Automotive Repair, to catch all those crooks.
Yeah.
Okay? But the rules they follow are the same rules the Maytag guy has to follow or anyone else. You got to have an invoice. You got to have a quote. You got to have sort of all these parts and pieces in doing proper business. And if you don't do that, the owner of the vehicle, the Maytag, the whatever it is, after you fix it, can come up and pick it up and drive away and not pay you a dime. They're not obligated to. Okay, so you kind of, and we don't teach that here because we're an FAA program, but you do have to follow the same business profession codes that every other business and profession has to follow. And in truth, more importantly than the legal side of it is, you want your customers to be happy with you, because then they come back and they come back and they come back, and that's what pays the rent, them coming back. Okay. All right, so there I am, the human test lead. I just bypassed it. If you can get to it, it's pretty easy. Okay? I got to figure out, is this field on the negative or the positive side? If it controls on the positive side, then I'm going to go field and either generator or battery, it doesn't really matter. Boom. If it's sitting on the negative side, I'm going to go field and ground. Okay? Real simple. whoa, voltage goes way up. Okay, I know it was the regulator.
Are all the pins labeled as such?
That particular one they are.
Okay.
But you guys being sophisticated, savvy electrician mechanics
Thank you.
ought to be able to look at that thing and in a few minutes and easily and quickly establish how it's wired. Or look on the airplane schematic and see how it's wired. Where are we? So yeah, again, if it's internally mounted, good luck with that. But if it's internally mounted, it's probably an automotive unit. Now, before we jump into the break, I will tell you one area that's bothered me a lot is in the world of experimentals, and there's a lot of them out there. There's, RV alone, Van Grunsven's RV, they're up to about 10,300 airplanes flying. Okay, that's a lot of airplanes being produced by one kit manufacturer. Well, for many, many, many years, it took me and a couple other guys a while to convince them to stop selling these. They were selling these reconditioned Nippon Diesel alternators, light duty little 35 amp alternators. Well, first off, they weren't continuous duty 35 amp alternators. Problem A. Problem B, those alternators, like every other alternator, has an internal fan. Guess what? What's true about automobile engines?
Oh,
All automobile engines, with the exception of some of the Honda models, spin the opposite direction from airplane engines. So the little fans weren't cooling. They're going the wrong direction when bolted to an airplane.
my
So now your capacity to be a pseudo 35 amp alternator has been compromised even more
By excessive heat.
by not enough cooling, right? Okay. Third problem, and Van's even produced multiple schematics for this. They already have an internal regulator, but Van's schematic and everybody who's anybody says, "Oh, we've got to put a voltage regulator in there." So they bolt the voltage regulator onto the firewall, hook it up to this one extra lead that they have in there, and then that would feed the power to the additional voltage regulator. So essentially, all they did is they said, "All right, let's just put our second voltage regulator in there." Well, you don't think that didn't confuse things? All kinds of problems. I literally sat down with their general manager, started drawing him diagrams and showing him, pulled it right out of the manual. He was impressed that I figured out what car that particular generator that they were selling had come from. That this is what you're doing. You really want to keep doing that. I think they now recommend a true aircraft alternator for all airplanes. It costs quite a bit more, but. And the only reason I did it is because I ended up having to fix about 15 or 20 different friends of mine with airplanes because they had used these things. So, and I'm just dumbfounded. Like 1 out of 20 mechanics in the world understand how an alternator and a voltage regulator actually work. It's profound the number of people don't understand how this system works. You guys need to understand if you want to be a decent technician. But if you do understand this, hey, write your ticket. Where do you want to work?
I'm confused how you wind up with a Lycoming or Continental motor and then like a car alternator. How did that?
It's
We
cheaper.
just bolt it on.
I know, but how did that? How I don't understand.
So AC Delco produced many, many alternators. Cessna said, why would I bother producing an alternator when I can go buy one from AC Delco? All I got to do is make a mount that bolts onto my engine. Okay, the pulley is a pulley is a pulley, right? So all I've got to do is get Lycoming to make a pulley diameter the right diameter, make the right size V-belt, buy a bunch of these from AC Delco.
and they passed.
Well, no.
Okay.
Well, the FAA doesn't have a choice. Cessna's the manufacturer. Okay? Well, Cessna said, yeah, we don't want liability, so they said, AC Delco, here's the QA process you're going to do. So even though the alternator may look exactly the same, it's probably built to different specs. At the very least, to different quality assurance specs. Okay? But are the parts probably the same in some cases? Are the bearings probably the same? Yeah. Brushes I know are different. The rectifier is different. The field winding is the same. Okay. In the world of experimental,
nobody cares, right?
right?
Now,
Okay,
other
all you gotta do
than
is make a bracket, bolt it on.
other than the cooling fan, the rest of it doesn't matter which direction it turns, right?
Remember we said all generators produce AC
Right,
until it's converted. Well, it doesn't care which way it's going. It's producing AC.
except for the cooling fan in that case.
And the cooling fan, and
Didn't properly cool the alternator.
if you look at it, yeah, let's use this one. This here, I think this is actually, this is probably a Hitachi generator. Note the little cooling fan. Okay, a
On the
little
inside,
cooling fan. This
internal,
cooling fan going this direction is going the wrong direction. Okay, the angle of the blades are trying to pump air inwards, but no matter what, this is always, because of centrifugal force, going to be trying to throw the air outwards, even though the blades are oriented wrong. If it spins this way, now not only is centrifugal force making it go the right direction, but so is the orientation of the blades, right? So let's
pulling
look
air
at
into it.
the way. No, right now it's throwing air out.
Out.
Pulling air in and throwing it out here.
Okay.
So if it's spinning this way, which way is the propeller spinning? This way. Okay, is that the right direction for airplanes?
No.
No, that's the wrong direction.
Why
for
not just
airplanes.
make the internal part just the opposite?
Yeah, just reverse it.
Why not?
Why not?
Why not?
Because
Good question. That's why mine, I went and got one of these rotors from a Honda unit, where the blades face the other direction. Fit it right in there. I'm golden.
Well, why doesn't a van do that?
Because they were just buying these things off of, from a reconditioner who didn't know any better.
Savages.
And of course, once they started looking and saying, oh, I gotta go buy a new Honda rotor and some other new parts to make this actually work right, now your cost is already getting up into the world of, might as well just go with an aircraft unit. Okay, I literally had to take pictures and one of these and stick it in a guy's face in the middle of a bunch of front of a bunch of other people. Embarrassed the hell out of them, but like, look, what you guys are doing is dangerous. You're gonna kill people if you haven't already. Now that you know it, please know, if I hear of an accident that has anything to do with it, I will inform them and I will inform their lawyers. It's the rabbit hole I went down. That you have been told and that you are the cause of this accident.
Lawyer is the key word there.
I got, well,
That's what got his attention.
I got his
Lawyer-
attention.
Oh, wait a second.
I suspect they were already starting to figure it out.
Does the Honda engine turn opposite as the rest of the cars or just the alternator?
I don't think it's, well, no, the engine goes, they're bolted in the same direction. There is a bunch of Honda engines that spin the opposite direction. There are also some that spin normal,
Okay,
spin automotive normal.
okay.
All right, so we ran a little bit long. Let's say we come back at a quarter till.